Let us switch over to the problem number 33. Let me read out the question first. R1, R2 and R3 are different values of R. A, B, C are the null points obtained corresponding to R1, R2 and R3 respectively. So what is this description actually he is giving? This is the application of meter bridge. He must be performing an experiment using meter bridge by applying different resistances in the resistance box. When in the resistance box, when the resistance is R1, he is giving us the balance point is obtained at A. When the resistance is R2, the balance point is obtained at B. Similarly, when the resistance is R3, the balance point is obtained at C. That is what has been given in the description. Now what is the question? For which resistor the value of X will be the most accurate and why? We just have to give the reason as well. Most accurate is the concept. Let me just give you the construction what has been given to us. If you look at, this is what has been mentioned as the meter bridge. Look at this one, the case. And he has given us, there is a resistor over here, there is a resistance box over here. From here, that is the middle screw, that connecting terminal, what we people are talking about. This is now connected across the galvanometer and connected to the jockey. This is a point A given, this is a point B given, this is point C given. This is the unknown resistance according to him. It is given as X. This is a known resistance, what is given as R. But all of you can understand, when the resistance in the resistance box is R1, the balance point is obtained at A. When the resistance in the resistance box is R2, the balance point is obtained at B. Similarly, when the resistance in the box is R3, the balance point is obtained at C. That is what has been the description in the question. Now the question is, when will this value of X be more accurate in all the three different cases? One should understand a very simple theoretical point. In a meter bridge, when the balance point is very close to the midpoint on the wire, the total length of the wire, of course, we know very well, that is 1 meter, exactly 100 centimeters. If at all the balance point is very close to 50th centimeter, the accuracy part of that instrument is going to be maximum. Reason better can be understood like this. The bridge is perfectly balanced when the balance point is exactly at 50th centimeter. If you just look at the values what he has given or the points what he said, A is one balance point, B the second one and C the third. By common sense and general idea, one can understand that this point is either right at the midpoint or very close to the midpoint. Either that or this. So certainly out of all the 3 points, this is a better option for us. So you should understand, when the balance point in meter bridge experiment is very close to the midpoint of the wire of length 1 meter. That means if it is very close to 50th centimeter, then the accuracy part of it is going to be the maximum. So what you should understand here, out of all the 3 points, the better choice is going to be B here. So if you look at the options given, first option is given A, second option is given B, third option is C, fourth option either A or C, anything like. The point here is very, very clear, it is going to be B. So remember, in a meter bridge, when will the meter bridge be perfectly balanced? If you find the null point exactly at 50th centimeter there. That is a theoretical logic by means of which you can identify the right option as B in this particular question. So this is problem number 33 what we have in this order. Look to the next problem, that is problem number 34. A circuit is connected as shown in the figure with the switch S open. When the switch S is closed, the total amount of charge that flows from Y to X is how much? In this particular circuit, what has been mentioned here, we have 2 capacitors connected in series and 2 resistors which are also connected in series, and the total system is connected across a cell of potential difference 9 volt. Let me just give you the circuit over here once again. There is a capacitor, there is another capacitor here. This is given as 3 microfarad, this is given as 6 microfarad, and here is a resistor, here is another resistor. Once again, you can find a switch, that is a key that is arranged in between these two. The resistance values are given this way. This is 3 ohm and this one is 6 ohm. And this total arrangement now is connected across a cell like this. What is the potential difference of this particular cell? What it can provide us is given as 9 volt. So the potential difference is 9 volt. This is one capacitor of 3 microfarad. This is the other capacitor of 6 microfarad. These two are the resistances. One is of 3 ohm and one is of 6 ohm. But what is his question? He is giving you this is the point as X and this is the point as Y. From Y to X, how much charge that flows? That is the concept. Under what condition he is mentioning that? When the switch is closed, then what happens? That is the idea. So one thing you should understand straight away. Capacitors, when I consider C1 is to C2, which now is going to be 1:2. You can straight away understand 1:2 is the ratio. When C1 is to C2 is 1:2, what would be the ratio of potential differences across them? If I take the potential difference across the plates of the first condenser as V1, if I consider across the second condenser as V2, what would be the ratio there? Since both are connected in series, we be knowing that the charge that remains constant on them. When charge remains constant, C and V are supposed to vary inversely with one another. C is inversely proportional to V, or even vice versa. V is inversely proportional to C. So if I write V1 is to V2, that now becomes 2:1. You can now understand 2:1 means what? 2 parts for the first one and 1 part for the second. Overall, 3 parts I can count them like. This total voltage now is supposed to be distributed in this ratio across these two capacitors as such. So what I can write now? V1 must now be equal to 2/3 of 9 volt. Why 2/3? We can understand total 3 parts, out of the 2 are given to that. So 2/3 of 9 is now going to be 6 volt. Likewise, V2 now becomes 1/3 of 9. That again is 3 volt. Then according to this particular pair of values, what we can understand is what would be the charge on the first capacitor. You directly can understand what will be C1. C1 is equal to C1, that is the corresponding charge. C1 is Q1, I directly write. Q1 is equal to C1 V1 I can take. Charge I am calculating. C1 V1 now will become 18 microcoulomb. Likewise, Q2 becomes C2 V2, that also becomes 18 microcoulomb. Reason better can be understood, these two are in series, I have already told you. The moment you are taking that, the system is open, means the switch is open. Firstly, he is talking about that. When the switch is open, the possible values of charges on both the capacitors are like that. In the sense, since they are in series, like 18 microcoulomb charge is appearing on the first capacitor as well as on the second. That is the concept. But what is the question now? When the switch is closed, when you close the switch, certainly current flows. But what happens is, no current that enters into this branch of the circuit. So certainly current enters this way and it goes like this. That is what you have to understand. So what will be the current that is passing through the system? That is going to be same, because you can understand 3 and 6 in series. Total will be 9 ohm and 9 volt is PD. Then what will be the current there? 1 ampere. So straight away you can understand the current across this one is 1 ampere. In fact, that we don't want it here. What we just want is what will be the ratio of their resistances. If you take R1 is to R2, now becomes 1 is to 2. But what would be V1 is to V2 now? This is also 1 is to 2. Because V is equal to IR when I consider Ohm's law. I is constant when they are connected in series. So V and R are supposed to be directly proportional to each other. When I take 1 is to 2, this implies what would be the potential difference across the first resistor of 3 ohm. It will now be V1. V1 becomes 1/3 of 9. That will now be 3 volt. And what would be V2 now? That will now be 2/3 of 9. That must be 6 volt. Now observe carefully. The moment you are keeping the switch on, then you can understand these two are in parallel, these two are in parallel. So what you should understand, whatever is the PD across this, same will be the PD across this capacitor also. What is the PD across the first one now? It is now 3 volt. That is what we have calculated. What is PD across the second one now? It is now 6 volt. That also has been calculated. So according to this 3 volt, it gets some charge. So what will now be the charge Q1 dash on the first? It is 3 into 3, that will be 9 microcoulomb. And what would be the charge on the second one now? Q2 dash. It is 6 into 6, 36 microcoulomb. Now just observe and compare these two values with the earlier values. How much it was supposed to be earlier when it was open? 18 and 18. Now it has become 9 here and 36 there. Very simple. Look at, it is now becoming 9. This is now becoming 36. That means how much has already gone from this one? It was earlier 18. Now it is 9. So how much that has gone over there? 9 microcoulomb has gone out of this one now. And this is now 36. That means earlier it was 18. So 18 once again is added to that. So what is it you are going to get? The charge of 9 microcoulomb over here and 18 microcoulomb over here, that is now entering onto the second. So what will now be the total charge that is passing across this yx? What will be the total charge now? That charge that is passing across yx now should be 9 plus 18. How much it will now be? 27 microcoulomb. So what charge that is passing through the system is the question. So it should now be 27 microcoulomb. What you can understand, look at the options given first. First option is given 0. Second option is given 54 microcoulomb. Third option is given 27 microcoulomb. And fourth option is given 81 microcoulomb. So which one is the right option over here now? It is a third option which is going to be correct. So we can say the answer for this particular question as such is going to be C like. It should now be 27 microcoulomb charge that now flows from Y to X as such. That is the concept you need to understand. Let us switch over to problem number 35. A part of circuit in a steady state along with the currents flowing in the branches, the values of resistances, etc. are shown in the figure. The energy stored in the capacitor of 4 microfarad is how much? 4 options once again have been given. First option 144 microjoule. Second option 288 microjoule. Third option is 72 microjoule. And fourth option is 36 microjoule. So what is the correct option over here means, according to the directions of currents and all, it should be the second option. That means it should be 288 microjoule as such. How come? Let me once again draw the entire part of the circuit what has been given over there for us. There is, of course, this is problem number 35 we are talking about. There is a cell first. It has been started with that. The cell is of 4 volt. Then you are finding 4 resistors. In fact, 5 resistors are connected this way. One resistance this way, the second resistance like this, third resistance this way, again one more resistance like this, one more resistance like this. And there is another resistance also that has been given over here like this. And he is just connected a capacitor C of 4 microfarad across these 2 points. And one more resistance is connected over here this way. And he has showed us the direction of current like this. And there is one more capacitor, this one cell, which is connected this way. Right? Let me just write the values what have been provided to us. If you check this one, it's 4 volt. This is given 3 ohm, the resistance. This one is 5 ohm, it's given. Likewise, this is 3 ohm, once again it's given. And what about the other resistances mentioned over there? Look at, it's 1 ohm, 3 ohm, 2 ohm and 4 ohm. It's 1 ohm, 3 ohm, 2 ohm and 4 ohm. And one more resistance that is mentioned over here as 1 ohm again. And the other battery what has been mentioned here is of 3 volt. And what are the values he has mentioned? 1 ampere of current is entering this way, 2 ampere of current is entering this way. That's what has been given. You take this point as A, this point as B. And 2 more currents he has mentioned. This is 2 ampere of current that is entering once again this way, and 1 ampere current that is entering this way. So according to him, this is now 3 ampere of current. That's now coming all the way. This is 3 ampere of current. That's coming all the way. Both put together in the form of 6 ampere, it's leaving the circuit like this. In fact, it is not a single or a closed network. You people should understand, it is a part of a major circuit. A small portion that has been mentioned for us to calculate what is the energy that is stored in the capacitor as such. One thing you should understand from this circuit, if at all you want the energy stored in this, then what you should do? You should calculate the potential difference across the capacitor. What is the reason? You can directly take energy as half CV square. There is a formula directly. C being the capacity, V being the potential difference across the plates of the capacitor. So C already is known to us. We just have to calculate the potential difference across these 2 points. Let us first of all apply second law of Kirchhoff. This is the network what I am taking up. So let us start from here. It is a potential at A minus 3 ampere of current is flowing across 5 means minus 5 into 3. This is IR. Next here also 3 ampere that is flowing. So minus 3 into 1. Here current is moving against my direction. So I should consider this one plus this ampere, 3 ampere once again, it is 3 into 2. And of course here minus VB, that now must be 0. So what you can understand from this one is VA minus 15 minus 3 plus 6 minus VB is 0. This gives you VA minus VB is now going to be 12 volt. Observe this wording carefully. VA minus VB is 12 volt, I said. That means what? You can understand that is the potential difference across the plates of the capacitor. This itself is the PD across the capacitor plates. So what will now be the energy part of it? It is half CV square, half C being 4. V square now is going to be 144. This goes twice. So you are left with 288 microjoule as such. So what is the total energy that is stored in the capacitor? Suppose if they ask you, you just have to apply the concept of second law of Kirchhoff, calculate using that second law what is the potential difference across the plates of the capacitor. That of course we have got it as 12 volt here. After getting the 12 volt there, half CV square formula we all know that is for the energy stored in a capacitor. That is in fact in the form of potential energy also, even that also every one of us we know. Therefore, according to the 4 options given over there, which option is tallying with this number? It is the second option which is tallied with this. Therefore, we can remember the answer for this particular problem is B now. So that is problem number 35 we have in this order. Next problem is Problem number 36. It is also one of the interesting models. An electrical circuit is shown in the figure. The potential difference across a resistor of 400 ohm as will be measured by the voltmeter of resistance 400 ohm is how much? As usual, 4 options are given here. One is 5 volt, the first option. Second option 10 volt. Third option 15 volt. And fourth option it's 2.5 volt. The correct answer for this one is 5 volt. That is the first option. Let us check first of all what has been the circuit that has been mentioned over here. He is just giving us 3 resistors which are connected in series like this in the system. And all the 3 resistances, when he has just connected one more resistor over here. What are the values he has just connected or taken over here? This is 100 ohm. This is also 100 ohm he gave. Okay. And other values, if you look at, this is 200 ohm that is given. Here is another resistance like this that is connected across. This is also 200 ohm. And across this, voltmeter is connected this way, right? So that is what actually is been given. Right. And this resistance in fact is given 400 ohm. This is also 400 ohm given. Now what is the remaining circuit over here? Here he has just connected a cell and it is connected like this. This is again 100 ohm. So if you just look at the numbers once again, totally there are 5 resistances. 100, 100, 100, 200, 400 here, and voltmeter of resistance 400 ohm again is connected. And here he gave 10 volt cell is connected across. If you just look at this circuit a little carefully, you can find a Wheatstone bridge in that circuit. Where is it? If you consider voltmeter of 400 ohm connected across another resistance of 400 ohm in parallel. In fact, we all know voltmeter will always be connected in parallel. So we know here this 400 and 400, when both are in parallel, what would be the effective resistance of that one now? Simply 200 ohm. So if you recollect once again that Wheatstone bridge, and if you compare that one with this, you will come to know that this is a replica of that Wheatstone bridge. How come? I just draw the same circuit again like this. Look at 100 resistance, second one, the third one this way, and here we have a resistor connected across. Here we have another resistor connected across, and this total system now is connected across the cell like this. This is of 10 volt, negative, positive. This one is 200 ohm. This one is 200 ohm. This one is given 100 ohm. This one is given 100 ohm. And even this one also is given 100 ohm. So you can even represent the same with a slight marginal variation also. You can connect even this one like this also. There is nothing in that. But look at carefully, this is the first branch. This is the second. This is the third, and this one the fourth. And this resistance is in place of galvanometer, whatever we find in a Wheatstone bridge. And we know the balancing condition of a Wheatstone bridge. Whenever the bridge is perfectly balanced, there will never be any current across the galvanometer. In fact, that is the condition for us to say that the bridge is balanced. Now even here also, when P by Q is equal to R by S, if I apply that equation, and when the equation is satisfied over here, then certainly you can say there will be no current across this 100 ohm resistance. There will be no current across this 100 ohm resistance. That is what you just have to understand. So what we can say now? These two are in series. These two are in series. So what happens in this particular case? Both are in parallel. Current whatever is entering here, it directly goes there. Current whatever is entering here, it directly goes there. So what you can understand this way, if I consider that this is 200, this is 100, 200, 100, like, the effective resistance can be calculated. So what you will be able to understand here is, you need not even draw this one also. You can directly also understand that one from this system. The moment you observe that, right, the effective resistance of these two, it is 100 again. So you can understand that 200 and 200 in series, 100 and 100 in series. Both are now in parallel. So what you should understand here is, what is the voltage across this is the question. So when you are talking about these two resistances like this is now 10 volt across. 200 ohm here, 200 ohm here, 100 ohm here, 100 ohm here. This is a 10 volt. You can now understand that this total value is 400 and this total value is 200. So what will now be the total potential across this one will be 10. Total potential difference across this one also will be 10, because they both are connected in parallel. When they are in parallel, this potential difference across this system is 10, across this branch also 10. Then how much will be the potential difference across this part? It will be 5 volt. This also will be 5 volt. And you can understand well, here is the voltmeter connected across. What will now be the voltmeter reading? That is the question there he is asking. Then what will be the voltmeter reading? Obviously, that now becomes 5 volt here. So you can say straight away take up the total potential difference across this resistance itself is the potential difference that is measured by that voltmeter over there. So what we can write now? The total PD or voltmeter reading, that is now going to be simply 5 volt. So voltmeter reading 5 volt is now tallied with the first option that has been mentioned there. Therefore, we can directly write the answer for this one as A. So only thing you should understand from this type of a construction, is there any clue like? The clue is what in this particular case? This particular construction is a replica of Wheatstone Bridge. If you can identify that one, it would be very, very simple and easy for you to analyze what exactly the value he is asking for. So this is problem number 36, of which the correct answer is 5 volt, that is tallied with first option for us. Let us check the problem number 37. An electric kettle has 2 coils. When one coil is connected to the AC mains, the water in the kettle boils in 10 minutes. When the other coil is used, the same quantity of water takes 15 minutes to boil. The time taken by the same quantity of water to boil if the 2 coils are connected in parallel is how much? That is a concept. And options are given this way. First option is 6 minutes. Second option is 12 minutes. Third option is 18 minutes. And fourth option is 24 minutes. In reality, understand my wording, in reality, if they give the same question or same model question at JEE level, in my opinion, no one need to work out the problem anymore. What is the reason? The options are so given that one can understand the answer directly without doing the problem. What is the reason? What is the concept behind? One coil when it is used, that means the first coil when it is used, we are finding the water is boiling in 10 minutes. When the second coil alone is used, the water has started boiling after 15 minutes. So with the first coil, it took 10 minutes for water to boil. For the second coil, it took 15 minutes for the water to boil. Fine. Now both are connected in parallel. That's what has been given. Then whatever time they are going to take together to boil this water, that time must be less than both the values of individual coils. First coil is taking 10 minutes, second coil is taking 15 minutes. When both are connected in parallel, our answer is supposed to be less than 10 and 15. That means less than 10 only. So if you look at the options carefully there, first option is the only one which is given as 6 minutes there. Second one is 12. Third one is 18. Fourth one is 24. So what we can understand here? The first option itself is the correct option for us. It took simply 6 minutes for us. But okay, that is the way we people used to tackle problems sometimes. Without calculating anything, just by the application of theory behind that, we used to estimate the right option. Fine. But we also need to know how to solve the problem. That is also equally important for us. So a kettle, of course, it's an electric kettle he is talking. It has got some quantity of water. Using the first coil, he has boiled water in 10 minutes. So what we can understand first of all here, look at carefully, we know heat energy generated over here is V square T by R. Actually V square by R, that is power. You can understand well, power, electric power, we have discussed 3 different formulae earlier. One is VI, I square R, V square by R. So power into time, that gives you work done. Work and heat energy are equal in SI units, we know that. They do have the same units as well. So H is equal to V square T by R. That is what actually we have to consider. So what we can write from this one now? It can be written R is equal to V square T by H as such. So what we can understand in this particular case is time has been taken as 10 minutes over there, and second one it is taking 15 minutes over here. Both are now connected in parallel. That is the concept. So what we can understand from this one is R1, if you take resistance 1, it can be taken as V1 square T1 by H. That of course you can even write V square T1 by H. What about this R2? This is now V square into 10 by H. What about the second one? It is R2, V square into 15 by H. So from these two, you can directly understand R1 by R2 is 2:3 ratio. Now what you can understand from this? When they are connected in parallel, what would be the effective resistance? R1 R2 by R1 plus R2. You can understand if you take proportional like it is 2 times 3 by 2 plus 3, it's now going to be 6 by 5, 1.2 ohm as such. Proportional if you take. Now you can write what will now be the quantity of heat energy in this particular case. It is V square into R parallel divided by V square into T by R parallel. Look at this step carefully. V square into T by R parallel, you can write it like this. Now you take the first equation and this equation and compare them like. Then what can we write now in this particular case? This is H1. H1 is equal to V square T by R1. And this H effective is equal to V square T by R effective. And what is this R1 we can write here? This can be taken as R1 is proportional to 2. Now I just take the ratio there. What will you get under this particular concept? How much time it takes is the question. So what time it takes in this particular case? R is proportional to the value of T here. So what can we write? R1 is proportional to 10. So what can we write here? R1 by R effective is equal to 10 minutes by this value of R effective is how much we people have got? That is T. So what can we write? 2 by 1.2 is equal to 10 by T. Then what will be T now? It's 12 over 2, which now becomes 6 minutes over here. So you can directly understand the concept here. R is directly proportional to T. Even you need not calculate all these things also. Directly also R1 by R2 is T1 by T2. In this case, R1 by R effective is equal to T1 by T effective. Calculate what is the value. Of course, unless you take the ratio, you cannot estimate what are the corresponding values of the resistances there. So what is it you people are getting? Time taken by them to boil water when both the coils are connected in parallel. That's the question he is asking. So how much we people are getting here? 6 minutes. Suppose if that fellow says both the coils are connected in series, then what to write in place of R effective now? R1 plus R2 we have to take. That in this particular concept it becomes 5 over here in place of 1.2. If I take this one as 5, it is 50 by 2, that's 25. That means what is the basic thing you people should remember? When coils are connected in parallel, time taken by them together to boil water will definitely be less than both the individual values of the coils earlier they have taken up. When they are connected in series, then what happens? The time taken will definitely be more than both the values. So that is actually the point what you have to remember. Another thing also you can do roughly. Of course, rough calculations sometimes we used to make it. What is the concept here again? 10 minutes for the first, 15 minutes for the second. 10 into 15 by 10 plus 15. R is proportional to T, you can understand. So 10 into 15, 150, by 10 plus 15, that's going to be 25. 150 by 25, how much time it takes? Simply 6 minutes, over. So you need not even go by this method also. But of course, you need to know the method along with the shortcut there. So shortcut, what is the concept here? R1 R2 by R1 plus R2 is the effective resistance when resistances are connected in parallel. Correspondingly, I can give the effective time taken will again be T1 T2 by T1 plus T2. So what is T1 T2? 15 into 10, 150. What is T1 plus T2? 10 plus 15, it's 25. 150 by 25, surely it will once again be 6 minutes. So what is the shortcut here? Look at now. R effective is equal to R1 R2 by R1 plus R2. Then what will be time effective? It is T1 T2 by T1 plus T2. This is 10 into 15 by 10 plus 15. That is 150 by 25. Exactly takes 6 minutes. So you need not even do this much. Straight away also you can do it. Remember, this is the shortcut for this type of a model. Suppose if they say they are connected in series, then write here R1 plus R2. Here you write T1 plus T2. How much it will now be? 10 plus 15. It will be 25 minutes. So this is actually the concept of problem number 37, where the option is tallied with the first option, that is answer is A now. 6 minutes will now be the correct answer for this question number 37. See the next question now. Problem number 38 I am talking about. When a battery is connected across a resistor of 16 ohm, the voltage across the resistor is 12 volt. When the same battery is connected across another resistor of 10 ohm, voltage across it is 11 volt. What is the internal resistance of the cell in ohm? 4 options are given. 10 by 7 ohm, first option. Second option, 20 by 7 ohm. Third option, 25 by 7 ohm. And fourth option, it's 30 by 7 ohm. The correct answer for this is 20 by 7, which is the second option for us. But look at first of all, what is he talking about? A resistor is taken up. A cell is just connected across this. Whenever we take this EMF of the cell as E and internal resistance as R, this is the external resistance as such, then you can certainly understand the effective EMF of the system becomes E, and effective resistance of the circuit is R plus R. Then you can write the total current becomes E by R plus R. That's okay. Then if I call the terminal potential difference across the resistor is V, terminal PD I am talking about, that's value is given V, then what can we write now? V is equal to IR, which now can be written I into E by R plus R. In fact, this formula we people just have to take up to work out that given problem. So it is nothing other than the terminal potential difference that is mentioned in the problem. It's not EMF of the cell. So what is the thing he has given once again? Let us look at. When a battery is connected across a resistor of 16 ohm, the voltage across the resistor is 12 volt. 16 ohm and 12 volt. Then how to write this equation? 12 is equal to, right, the value of current into E, that is, you can directly write R plus small r, the internal resistance is asking you. 12 volt he has given you, IE by, that is E by R plus R, into capital R, we should write here, RE by this R plus R. Look at once again carefully. 12 is equal to RE by R plus R. But what is R given here? 16. So I write the first equation. Look at 12 is equal to 16E by 16 plus small r. That's my first equation. Exactly like that, look at the second one. When the same battery is connected across another resistor of 10 ohm, voltage across it is 11 volt. So what should we write now? 11 is equal to 10 ohm, he said. Directly it is connected across a 10 ohm resistor. So we can write 10 times E by 10 plus R. That's my second equation. So all of you can understand IR, that is E by R plus R into capital R. That is the formula. That I have repeated twice according to the values which are provided to us. Now take the ratio please. 12 by 11 is 16 by 10 into 10 plus R by 16 plus R. Of course 3 times 4 and 4 times 4 here. This twice you can cut and 5 times over here. This now becomes 3 by 11 is equal to 20 plus 2R by, right, 80 plus 5R. Come on, cross multiply that one now. It will now be how much? It is 240 plus 15R is equal to 220 plus 22R. 3 times 80, 240 plus 15R is 220 plus 22R. Now bring this one this side, you can directly get 7R is now going to be 20. Then what will be R? 20 by 7 ohm. Look at this calculation carefully. So what must be the correct answer for this? 20 by 7 ohm must be the internal resistance of the cell that is used in both the cases. Which answer that is tallying with that? Look at first option 10 by 7 is not correct according to this. Second option given as 20 by 7 ohm. So what is the correct option? The answer for this particular problem is the second option, which is now B, that is 20 by 7 ohm as such. So this is problem number 38 what we have, and the correct option for that one is 20 by 7. So remember in this problem, whatever the voltage he is mentioning in each case, that voltage is supposed to be the terminal potential difference across the terminals of that resistance, external resistance in particular. That is the concept you need to understand. So this is problem number 38.